Alright, so today we're going to start talking about quadrilaterals. And we're going to start off with organizing into a Venn diagram the different types of quadrilaterals that we have. So we're going to start with a definition of what a quadrilateral is, and then we're going to build on those with special cases. So a quadrilateral is a four-sided polygon. So a polygon is a closed shape and I have four sides. That's my general definition for a quadrilateral. We see the quad deals with four. We have a special case. Our first type is a parallelogram, and our definition for parallelogram is a quadrilateral that has two pairs of parallel sides. So both opposite sides are parallel. Within that, we have some specific cases of parallelograms. So I have rectangles and rhombus. And where those meet in the middle, those are our squares. So a square is a rhombus and a rectangle and a parallelogram and a quadrilateral. It's our most restrictive case. There's two other types of quadrilaterals that we're going to look at as well, which are kites, quadrilateral, where two pairs of adjacent sides are congruent. It's in its own little category, so if I was to sketch it out, I have a shape like that. It looks like the kite that you fly around. And it is a subset of quadrilaterals, but nothing else. It's not a parallelogram. And then I have the trapezoid, which is a quadrilateral where I have one pair of parallel sides. And it is its own shape, its own subset of the quadrilaterals. So that's an overview of what these look like. And what we're going to do in this chapter is prove some properties of these quadrilaterals. All right, so let's look at a couple properties of parallelograms to start with, because that's our biggest section of this, where we have the most shapes that fall under parallelogram. So I'm going to be given a general parallelogram ABCD, and I want to show some properties of it. So I start with my general shape ABCD. To make it a parallelogram, I show that the opposite sides are parallel. And Theorem 6.1 tells us that the opposite sides are congruent. The way we're going to go about showing this, we're going to do kind of a mini proof, is we're going to use our triangle properties. So what we know about proving triangles congruent, we can then show with corresponding parts that the opposite sides are congruent. So proof, the y, we're going to basically show that triangle ABD is congruent to triangle CDB. And we're going to have to use one of our postulates to get there. Well, we know a lot about angles and parallel lines cut by a transversal. So I know 1 and 2 are congruent because they are alternate interior angles. I also know that 3 and 4 are congruent because they're alternate interior angles for the other set of parallel lines. And I know that line segment DB is congruent to itself from the reflexive property. Alright, therefore triangle ABD and triangle CBD are congruent from angle side angle. Hey. And our conclusion from corresponding parts congruent triangles are congruent is that DC is congruent to AB and AD is congruent to BC. We can also conclude something about the angles. So angle A is congruent to angle C, and in general opposite angles are congruent for a parallelogram. This is Theorem 6.2 within our book. Alright, well we can also investigate a couple more properties of parallelograms as we go through. So given, again, a general parallelogram, we want to prove that the diagonals are going to bisect each other. And so we're going to start with our general picture, ABCD, and to make it a parallelogram, we add our parallel lines to it. And what we're looking for is we want to show that E is the midpoint of both of those diagonals, or another way to say that is AE is congruent to EC and DE is congruent to EB. And again, we're going to use some congruent triangles to get there. So I know my sides are parallel because it's a parallelogram. And I'm going to use the same type of reasoning as before, where measure of angle 1 is congruent to measure of angle 2, measure of angle 3 congruent to measure of angle 4, because those are all alternate interior angles. And we know that they're congruent from our previous chapters. Well, I also know that AD is congruent to CB because we just proved that opposite sides of a parallelogram are congruent. And I have two angles and a side, which I can then conclude that the triangles are congruent because of angle side angle. And now that I have that, I can match up my corresponding parts, and I can conclude that AE is congruent to EC and DE is congruent to EB. So the diagonals bisect each other for a parallelogram. So 2 quick examples of how this might look in the book. Given a parallelogram where I know an angle, I want to also look at a parallelogram where I know something about the sides. So looking at number 1, I know that x plus 40 has to equal 180 because those are same side interior angles, and from our previous work with parallel lines and a transversal we know that they are supplementary. So just subtracting 40, I get x is 140. The other one, I know that opposite sides are congruent, so 12 equals 2x plus 4. Solve for x. X is 4. Plug that in for the other side, and you get that that side is 1, which also means the side opposite is 1. So that's kind of how we're going to use the properties that we proved. Alright, one other thing to just kind of touch on is if we're given that parallel lines make congruent segments for one transversal, then for all transversals they'll be congruent. So in our picture we have that AC and CE are congruent, which means that BD and DF are going to be congruent. If we were looking at a picture where I had congruent segments cut by a transversal, by parallel lines, I know that everything else in this case is going to be 2.5. So those are congruent to each other. Alright, so we have our flashcards that we started that you will add to as we go through this. I'm just going to do the first one here in this video. Parallelogram is a quadrilateral with both pairs of opposite sides parallel. And if we look at our diagram, that means that it's parallelogram. And I know that the opposite sides are congruent. We proved that. Theorem 6.1. I know the opposite angles are congruent. Theorem 6.2. And I know that diagonals bisect each other. So AE is congruent to EC, DE is congruent to ED, and that's Theorem 6.3.